Welcome back, students. This is the second part of this chapter 4, carbon and its compound. In the second part today, we shall start with the homologous series. What is homologous series? Homologous series is a series of carbon compounds, or it can be also said as organic compounds with similar chemical properties and some functional group differing from the successive member by a CH2 functional group. Such organic compounds that vary from one another by repeating units and have same general formula are called as homologous series. So homo means similar or same, and logos means the position. Means in chemistry, the organic compounds which occupy the same position as far as their chemical property, they are called as homologous compounds, and the series they form is called as homologous series. For example, alkane, they have a general formula CnH twice n plus 2, and the compounds can be like methane, ethane, propane, butane, pentane, hexane, etc. All these compounds, they form a series, and that series is called as homologous series. Similar to alkanes, there can be alkenes. Alkenes have the general formula CnH twice n, and therefore the compounds will be like ethene, propene, butene, pentene, etc. Similar to the alkane and alkenes, there can be another homologous series of alkynes, and they have the general formula CnH twice n minus 2. So they can form a homologous series like ethyne, propyne, butane, pentane, etc. So let us proceed with this. For example, you can see on this display that there is a series called as alkane series, and examples you can see there: methane, ethane, propane, butane, and so on, and they form a homologous series. You can see their structures. This is methane, this is ethane, this is propane. They are all saturated carbon compounds because between carbon and carbon there is single bond, and they are alkanes. And all these compounds that we can see here, methane, ethane, propane, they have similar chemical properties, and they have same, that is general formula CnH twice n plus 2. And most interestingly, between methane and ethane there is a difference of a CH2 group. Similarly, between ethane and propane also there is a difference of CH2 group. Similarly, below you can see a series of alkenes and alkynes also can form homologous series. We have seen here two compounds towards the end. You can see here on this second part of the slide here in this one, ethene and propene. These are the two examples we have given here. Here ethene and propene both belong to alkenes because they fall under the general formula CnH twice n. Between carbon and carbon we can see there is double bond, and due to presence of these double bonds they are unsaturated carbon compounds, and they form another homologous series, and that is called as alkenes. Now the characteristics of homologous series. The first characteristics we can see here in this display. Each member of the series can be represented by a general formula. That is just what I have already mentioned. Second, all the members of the series can be prepared by same general method. Number 3, the physical properties of the compounds present in the homologous series may slightly differ from each other. But number 4, we have seen all the members of the homologous series have similar chemical properties. So these are the 4 very important characteristics of the homologous series. Now the nomenclature of carbon compound, and this is present in your textbook after the homologous series, how we can name the carbon compounds. To give a proper name in science to the carbon compounds, what we have to do, we have to identify the number of carbon atoms present in the compound. We can see here it is at the beginning we have written to identify the number of carbon atoms in a compound. For example, in the saturated hydrocarbon, if we count the number of carbon atoms present, then it will help us to give their names. For example, if there is only one carbon atom is present in a saturated hydrocarbon, it is methane. Single carbon atom in a saturated hydrocarbon is methane. 2 carbon atoms, then it will be ethane. 3 carbon atoms, propane. 4 carbon atoms, butane. And 5 carbon atoms, pentane. So on. Similarly, an unsaturated carbon compound containing more than one carbon, maybe 2 carbon atoms or 3 carbon atoms, will accordingly be named. How? You can see if there is one carbon atom, then it is methane. But if there is 2 carbon atoms present in a unsaturated hydrocarbon, it is ethene, provided if it is alkene, and or it can be ethyne, provided if it is an alkyne. 3 carbon atoms will be propene, alkene, and propyne will be alkyne. 3 carbon atoms, then after that we are coming to the 4 carbon atoms present in a carbon compound unsaturated, then it will be butene, and if it is alkyne, then it will be called as butyne, and so on. So this is how we can give the name to the carbon compound by counting the number of carbon atoms present in the compound. But we can see the functional group present in the organic compounds are also used to give the names to the carbon compound. There is a chart you can see. In the chart you can see the functional group present or the atom present attached to the carbon chain. If chlorine is present, you can see here in the chart, this is chlorine. If chlorine is present, then a prefix we will have to use chloro. For example, in methane, instead of all hydrogen atom, one atom is chlorine, then it will be called as chloro, means chloromethane. Similarly, chloroethane, chloropropane, chlorobutane, etc. Bromine is present, number 2 you can see, then it will be bromo. For example, bromoethane, bromopentane, bromobutane. Apart from chlorine and bromine, if iodine is present, it will be iodomethane, iodoethane, iodopentane. Or if it is fluorine, then it will be fluoro, then fluoromethane, fluoroethane, fluoropropane, fluorobutane, etc. If the functional group present in the carbon chain is an alcohol group, that is OH group, then we will add not a prefix but a suffix. We can see here it is in the third one here, and you can see this is the suffix we will use all. For example, in methane, if one hydrogen atom is replaced by one alcohol group, that is the functional group is OH, instead of methane it will be called as methanol. If it is ethane, then it will be ethanol. Propane, then it is propanol. In that way, according to the alcohol group, the suffix OL is added at the end of the name of the compound. Similarly, if there is an aldehyde group, CHO group, then AL will come. For example, methane will change to methanol, ethane will change to ethanol, propane will be propanol, butane is butanol. Similarly, ketone group is coming. You can see here it is ketone group, then ketone group is double bond CO. That functional group is coming, then we will add a suffix ONE, one, on. And for example, methane will become methanon, ethane, ethanon, propane will be now named as propanon. And carboxylic acid group comes. Carboxylic acid, this is the single dash COOH group. We have discussed all these functional groups in our previous class. So you must have studied that part. So I hope you will understand this. Carboxylic group is added to the carbon chain, then will be oic acid. We can see the suffix we shall use here, oic acid, OIC, oic acid. For example, methane, it is attached to one functional group, that is carboxylic acid, then will be methanoic acid. Ethane will be ethanoic acid. Propane will be propanoic acid. And double bond compounds will be called as alkene, then ENE is used. For example, ethane will be ethene, Propane will be propene because double bond compound is there. It is alkene, so last three letters ene as a suffix will be added. And if it is alkyne at the last triple bond, then yne is used. For example, ethane will become ethyne. Propane will become propine. So accordingly, suppose if we consider methane in all the form, methane, chlorine is coming, chloromethane, bromine will come, bromomethane, iodine comes, iodomethane, fluorine comes, fluoromethane, alcohol comes, methanol, aldehyde comes, methanol, ketones come, methanone, carboxylic acid comes, methanoic acid, and if it is double bond, then it is suppose ethene, and triple bond it is ethyne. So in that way carbon compounds are named. We can see here is a chart given, and in this chart you can see the examples of propane. It is attached to chlorine group in the first, so it is becoming chloropropane. In the second was it is propane, bromine is coming and attached to the right hand side. You can see here chlorine was attached in place of hydrogen here, so it is becoming chloropropane. Here bromine is coming, so will become bromopropane. Here OH group is coming, so it will become propanol, alcohol is coming, and keto, this is aldehyde group coming, so propanol. So in that way we can be used. Coming to discuss the chemical properties of carbon compounds. Carbon compounds exhibit very interesting chemical property, and the first property is combustion. Combustion means burning. All carbon compounds can be burned. They can be burnt in presence of oxygen. When carbon is burnt in oxygen, they will produce water, and apart from water, they will always produce carbon dioxide gas, heat and light. You can see, for example, we have given here example, carbon is combining with oxygen in presence of heat, means carbon will burn in oxygen and will produce carbon dioxide, heat and light. In this compound, water is not formed. But in the second compound, you can see methane is a carbon compound combining with oxygen, means burning, will produce water, carbon dioxide, heat and light. Or you can say this is ethanol, ethyl alcohol, combining with oxygen, means burning in presence of oxygen, will produce same water, carbon dioxide, heat and light. So we call all these three reactions as burning or combustion of carbon or carbon compounds. So this is the first chemical property of carbon, that carbon compounds are combustible and they burn in presence of oxygen to produce carbon dioxide, heat, light and water. Coming to see oxidation. So what is oxidation? It is also the chemical reactions in which oxygen is added. So carbon compounds like alcohols, they are oxidized to carboxylic acids on heating with some oxidizing agents like alkaline potassium paramanganate, that is KMnO4, or it can be acidic potassium dichromate, K2Cr2O7. So let us see, for example, you can see alcohols, you can see here the cursor, you can see my cursor. The example is given here, alcohols are oxidized to carboxylic acids. How? This is ethanol, and you can see ethanol is changing to ethanoic acid. Why? Because we are adding some oxidizing agent like alkaline potassium paramanganate or acidic potassium dichromate, and if we heat in presence of any one of these two oxidizing agent, then alcohol will be converted to that is acid, that is ethanol is changing to ethanoic acid. So this is the second property. We have seen here the chemical properties of carbon. The first chemical property of carbon we have seen, combustion, and the second chemical property, that carbon compounds can easily be oxidized in presence of some oxidizing agents. For example, alcohols can be oxidized to acids. We are getting the chemical reactions performed by carbon compounds. Carbon compounds exhibit addition reaction and the second is substitution reaction. Now, what is addition reaction? Addition reaction is a kind of combination reaction where you can add something to a compound. But substitution reaction, here you cannot add something directly. Before adding, you have to remove something from there. So let us understand it by taking examples. You can see first, addition reaction is possible only in case of unsaturated hydrocarbon. This is very important. Now, unsaturated hydrocarbons undergo addition reaction with hydrogen in presence of certain catalysts like nickel catalyst or palladium catalyst, and in that way unsaturated hydrocarbons convert to saturated hydrocarbons. Now, you should know one thing, that unsaturated hydrocarbons are always have double bond or triple bond between two adjacent carbon atoms. That is why they can add more hydrogen atoms. For example, if we see this OH reaction, ethene, this C2H4, it is ethene and it is combining with hydrogen in presence of nickel catalyst and is producing ethane. Because two carbon atoms can hold 6 oxygen to form ethane, but in this compound 2 hydrogen were less. That is why it is unsaturated. So you can add 2 atoms of hydrogen or 1 molecule of hydrogen can be added to this compound in presence of nickel catalyst to form a saturated hydrocarbon. If we see the same thing in the structural formula, this is ethene. Between carbon and carbon, we can see this is a double bond, and to this carbon 2 hydrogen and to this carbon 2 hydrogen atoms are attached. Now we are bringing hydrogen, and now in presence of nickel they will get converted to this compound ethane, where this double bond has been converted to single bond. You can see here it is converted to single bond. It means the unsaturated hydrocarbon is now changing to a saturated hydrocarbon after this addition reaction. So this addition reaction is important because during this addition reaction we add hydrogen to an unsaturated hydrocarbon, and therefore these chemical reactions are called as hydrogenation. So this hydrogenation is used to convert unsaturated oils and fats to saturated compounds, saturated hydrocarbons. Coming to the second type of chemical reaction shown by carbon compound is substitution reaction, and this is possible only for the saturated hydrocarbons, because you see saturated hydrocarbons are already saturated with number of hydrogen atoms required by it. Therefore you cannot add any monovalent element to this saturated hydrocarbon until and unless you replace or substitute the hydrogen with the monovalent element. This type of chemical reactions are called as substitution reaction. So let us see, for example, methane, it undergoes substitution reaction in presence of diffused sunlight, and it can be added with chlorine gas. For example, we can see here this is methane CH4, which is a saturated hydrocarbon, and to this methane we are adding chlorine. But definitely this chlorine cannot be added to this compound methane. So what we need to do, we need to perform this chemical experiment or reaction in presence of diffused sunlight. Then chlorine will replace 1 hydrogen from this methane and will form CH3Cl. Earlier it was CH4. So from CH4 1 hydrogen is removed, and in place of that 1 chlorine has entered and has become CH3Cl. This is called as chloromethane, and hydrochloric acid is formed. This type of chemical reactions are called as substitution reaction. This chloromethane can again be added with chlorine to produce dichloromethane. This dichloromethane can be added with chlorine here in the third reaction to produce that is trichloromethane, or finally the trichloromethane can be again substituted with 1 chlorine to produce carbon tetrachloride or tetrachloromethane. So this is how the carbon compounds can show substitution reaction. Some important carbon compounds. The syllabus of class 10 science book says to study us the two important carbon compounds, and their number one is ethanol, ethyl alcohol, and its formula is C2H5OH. So we will directly come to understand their properties. Ethanol is a colorless liquid, colorless like water, with a pleasant smell. It is pleasant. I mean to say that it depends on people to people. It has a smell. In science, we call this is a pleasant smell, and it's a burning taste. So ethanol has this physical property. It is colorless liquid, it has a smell, and it is a burning taste. Second, it is also soluble in water. It is water soluble. And the third, ethanol reacts with sodium to form sodium ethoxide and hydrogen gas. This is ethanol. You can see the chemical reaction, C2H5OH, and if we bring sodium metal in contact with ethanol, instantly it will produce a salt, sodium ethoxide, and it will release hydrogen gas. It will release hydrogen. It is a property of metal that metals can react with acids and bases to produce salt and hydrogen. Similarly, we have seen here a metal, very reactive metal like sodium, is even reacting with alcohol and is producing a salt and hydrogen gas. Coming to the fourth property, ethanol reacts with hot and concentrated sulfuric acid to produce ethene and water. It means ethanol, this is C2H5OH, which is a saturated carbon compound. If you just bring this saturated carbon compound in contact with hot and concentrated sulfuric acid, it will convert to ethene, unsaturated hydrocarbon, and water will be released. So these are certain properties given in your book. Now uses. What are the uses of ethanol or ethyl alcohol? Ethanol is used for making alcoholic drinks, what we call commonly as wine. It is used as a solvent because many organic substances can be dissolved in ethanol, so it is used as a solvent. It is used for making medicines like tincture iodine. Many cough syrups, tonics, etc. always contains alcohol in it. Coming to the second important carbon compounds, and that is ethanoic acid, and the formula you can see CH3COOH, ethanoic acid, also called as acetic acid. Properties: ethanoic acid is a colorless liquid like ethanol and with a pungent smell, and it is sour in taste. Definitely it will be sour in taste because it is acid. It is a different kind of taste, and it is a colorless liquid. This is also soluble in water. So like ethanol, ethanoic acid is also water soluble. So we can definitely dissolve ethanoic acid or acetic acid in water. Now third property, if we make a solution of 5% to 8% ethanoic acid in water, then this mixture is called as a vinegar. That is to say that you have to take suppose 95 parts water or 92 parts water, and then remaining 5 parts or 8 parts acetic acid or ethanoic acid is mixed in that water, then the mixture formed is called as a vinegar. This vinegar is now becoming weak as far as its pH is concerned, and it becomes edible. So this vinegar is commonly used in our kitchen. It is used in making pickles and all. Coming to see in another interesting property, esterification. So esterification is a property of this ethanoic acid. So let's see this, what is esterification. Ethanoic acid can react with ethanol to form ester. So this ethanoic acid or acetic acid, if we can mix it with alcohol, it will form a compound, and that compound is called as ester. But this reaction will occur in presence of concentrated sulfuric acid. So you can see the reaction CH3COOH, that is called as ethanoic acid, also acetic acid, mixing it with ethanol C2H5OH, and these two will react in presence of concentrated sulfuric acid, will make it CH3CO CH3COO, then C2H5. This compound is called as ester, and along with this ester, water molecule is formed. This type of chemical reactions in which an acid and an alcohol combine together to produce ester is called as esterification. Esterification, important for your examination. Coming to see, saponification is another important property. Now, when this ester reacts with sodium hydroxide, now this is ester we have already formed. Now, this ester we are bringing to the next part. This ester is allowed to react with sodium hydroxide solution. Then a sodium salt of carboxylic acid will form. And this reaction now is called as saponification. For example, ethyl ethionate. This is the compound which is called as ester, ethyl ethionate. This ester is allowed to react with sodium hydroxide, and then it will produce a salt, sodium salt, and ethyl alcohol. This type of chemical reaction is called as saponification. Ethanoic acid also reacts with bases to form salt and water. Because it is acid, we have already come to know acids reacts with base and produce salt and water, and this is neutralization reaction. Similarly, ethanoic acid is also an acid, so will definitely react with base like sodium hydroxide and will produce the salt, and the same salt, this is an ester, and water molecule is produced. Next property, ethanoic acid reacts with carbonates and hydrogen carbonates to form salts, water, and carbon dioxide gases. For example, we can see here, this is the compound reacting with sodium carbonate, producing this, you can see ester, water, and carbon dioxide. This is again the compound acid, this is acetic acid reacting with sodium hydrogen carbonate, and the same compound is produced. So in this way we have found that ethanoic acid can react with carbonate or hydrogen carbonate to form salt and water. Coming to next part, that is soaps and detergents. Now, what are soaps? Very familiar to us, we use in our toilets, bathrooms. Soaps are long chains sodium or potassium salts of carboxylic acids. So what is a salt? It is nothing but a long chain sodium salt or potassium salt, but it is acidified salt, means there is always carboxylic acid attached to it. For example, sodium stearate, it is an example of salt, and this formula is, you can see, C17H35COONA, sodium stearate, and this is example of a soap solution. Now, what is the structure of the soap molecule? A soap molecule has two parts. This type of compounds have two parts. You can say this part, C17H35, it is a long chain of carbon. There will be 17 carbon one after another joining with each other by catenation. And there are 35 atoms of hydrogen which will remain attached to the long carbon chain. So this is a very long part. And finally, you will, at the end, you will get a metal, sodium metal. So the structure is like this. This is the long chain, you can say zigzag, that part you can see. This is the long carbon chain. It is the hydrocarbon part. This part. What the cursor you can see. Carbon 17, hydrogen 35, then carbon, oxygen. So up to oxygen. This is a very long part. And this round part is this part, sodium attached to COO. This part. So this is the ionic part, because sodium is a metal, will remain positively charged. Ionic part, and this part is called as hydrophilic because it is water attracting or water loving part. And this hydrocarbon chain, which is water repelling or water hating part, so we call it is hydrophobic part. Means this part of the soap molecule will remain away from water, but this part of the soap molecule will always remain with the water. Now, cleaning action of soap. How soap molecules can clean the dirt. That is cleansing action of soap. When soap is dissolved in water, it forms some spherical structures called as micelles. In each micelles, the soap molecules are arranged radially in such a way that the hydrogen and carbon part, means the hydrocarbon chain part, towards the center, and the ionic part, means this part, will always remain towards the outside. The hydrocarbon part dissolves in the dirt, which may be oil droplets, which may be grease or some other emulsions. This part always remain attached to the dirt. This long carbon chain, I am just showing it through my marker. This part of the soap molecule always will remain attached to the dirt by chemical reaction, and this part will always remain attached to water, and as a result they will form some special structures called as micelles. Now let's see how micelles are formed in water, and for that we have to see a video, and this video will help you to understand what micelles are and how they are formed.
The classic surfactant molecule. It has a polar head and a long carbon chain from a tail. For the sake of demonstration, we'll use a bit of shorthand and transform our surfactant molecule into what we call a lollipop. If we could see what was happening at a molecular level, magnifying the molecules over 1 trillion times, and we added our lollipops, our surfactant molecules, to a beaker full of H2O, the surfactant molecules immediately go to the interface, and the polar heads, doing what nature likes, are drawn to the polar water molecules. But when the surface is saturated, when no more surfactant molecules will fit, something really interesting happens. In a sort of dance, the excess molecules find each other. The nonpolar tails all want to be together, and the polar heads all want to be together. And they form spheres called micelles. Now I'm sure you're thinking, that's all well and good, but how does it help me? For that explanation, we'll turn to the most well-known surfactant on the planet, soap. That's right, soap is a molecule derived from fats that has, ta-da, a polar head and a nonpolar tail. So, if instead of a beaker of water, we have a glass that contains not only water, but also remnants of cooking oil, and we add our soap, or surfactant molecules, they do the same thing that they did before. But this time, the nonpolar tails of our soap molecules and the nonpolar oil molecules are drawn together. The oil is captured within the micelles and can now be easily rinsed away. But where do these miracle molecules come from? And how do we use them to help make our planet and your lives better? Evotherm Chemistry 101, coming up next.
Hope you have understood.
The classics.
You have understood this. So let us see this soap molecules. This is the container or a beaker, and we are having some water in it. When we will add the soap molecule in it, as I have already mentioned, this is the sodium ion. This is the part which is hydrophilic, and this long carbon chain is hydrophobic, water hating part. This is the long carbon chain. They always remain in this particular orientation. Since these parts, long chain parts, do not like water, they always want to remain away from water. So what happens, whenever in this water some dirt is present, oil is present, fat is present, grease is present, then the grease molecules will be attracted by these ends of the long hydrocarbon chain. So we can see here, this is the dirt particle, oil or grease, whatever it may be, it will be attracted by those long chains, and as a result what will happen, we will get a special formation. All the soap molecules will gather around this dirt particle. How? All the ionic part facing outside and the water hating part facing inside. Then this structure, whatever is formed inside water, is called as micelle. This is how soap molecule, you can see in the second diagram. This is the soap molecule, this is the hydrophilic part, water loving part, and this is the long chain. They will run towards the third and in the water they will combine in this way. You can say all this part, hydrophilic part will remain outside and hydrophobic part will remain inside, and in the middle this is the dirt. How soap molecules can take the dirt away from our clothes. This is how soap molecules can clean. Now detergents. Detergents are also long chain sodium salts of sulfonic acid. We got the soaps are actually the long chain hydrocarbons of acids, but what was that acid? Just see it back, you will get it here. The acid was here, you can see carboxylic acid. But here we have got in the second part, that is in case of detergent, it is instead of carboxylic acid, you can say this is sulfonic acid. Soaps do not wash well with hard water because it forms insoluble precipitates of calcium and magnesium salts in hard water, but detergents can. So that is given, the detergents wash well with even hard water because it does not form insoluble precipitate of calcium and magnesium in hard water. So there is a slight difference between soaps and detergent. Basically we have got that in soaps the acid present was carboxylic acid, but in detergent the acid present is sulfonic acid. Second thing, soaps always produce some precipitates of calcium and magnesium with hard water, means it doesn't give good lather. But detergents, they never produce those insoluble precipitates of calcium and magnesium in hard water. That is to say that they can produce good lather even in presence of hard water. So in this chart you can find the differences between soaps and detergents. I have already given you the PDF format of this entire slides where you have already got the difference of the soaps and detergents. So that was what one wanted to discuss in this second part of this lesson, carbon and its compound. Here the entire chapter ends. In our next online class we will start with a different chapter. Thank you.